let us talk about shear forces. Shear forces. We already talked about this a little bit. We usually call them V in statics. Uh, Sometimes they can also be tau, but that will be more in advanced classes when you learn about how to represent strain in three-dimensional coordinates in a point. More like in continuum mechanics or even in advanced materials or mechanical materials, etc. In statics, we mentioned that we only care about finding the forces that a system will see or endure. And from those forces, then we can design the materials, the shapes, because if you notice, we at this point did not care if this structure has a square um, profile or if it's more like um, I-type profile or if it's how deep or what's the length of the profile. So we don't care about those things at this point. We only care about given those forces, what are the supports or internal forces that we have to consider. Okay, so V as vector is going to be what we use for our shear forces. So when we have distributed forces, or even with concentrated forces, we want to make cuts through sections to be able to see what is the shear and normal force. So we already saw that in examples, what is the shear and normal forces, and the moment at that point. Okay. Um, but if you look at this as a continuum, you can really make a cut anywhere. So we're gonna learn today how to represent the shear forces and the momentum at any point with a few concepts. With concentrated loads, which we know in this case P1 will be represented by this rectangular distributed load, and P2, as we saw, could be because of this non-uniform distributed load that you can find using different techniques. All right, so let's review something before we move forward. We know by now that when we see beams in a problem, we have to first of all know how to place the restrictions. So this we've used many times is restriction in X and Y. This is a simply supported beam because only one point is fixed. The other one can roll. So this one is only in Y. Only has a force in Y. If this is point B, then you have to find those forces. But if it's point A, then you have a point A, X, and a force AB. I mean AY. Interestingly here is similar, but obviously you have to consider the difference in lengths. So this is called the overhanging beam. Then the famous cantilever beam, which you only use for an X and Y restriction here, everything else is free. And if you place a force here, this beam will deform like so. And if you place a force underneath and move up, the beam will displace like so, or deform like so. Okay. Then we have indeterminate beams, because in this type of beam, you have a force in Y here, a force in X here, but say this is point B. You have BY, and this is point C, you have CY. At this point, with the methods that we know how to use so far, we cannot determine the value of C and By and Ay. Why? Because say they give us two forces, distributed or concentrated, P1 and P2. For that case, summation of forces in Y, we have Ay plus By plus Cy and negative P1 and negative P2 equals 0. And Cx is pretty simple because we know that it's going to be 0. There's no other force in X. Okay, so we have one equation and three unknowns because P1 and P2 are given. They're the loads. And then say we do a moment around A. Then we have, this is L1, this is L2, this is the distance between A and B. And basically what I'm getting at is that you're going to have two forces with B and C that are unknown. So you have three unknowns and two equations. So this is a non, or this is an indeterminate beam because you don't know the forces at By. But you use these cases when, say, you start from here and the forces are too large. Then knowing that force, you can, determining By, you can say, oh, okay, well, we can break By in two and then say By half here and By half here. And then in that case, you can design that beam like that. But you have to start somewhere else. And from a design purpose, you can just add C or Y to your design. So I'm not going to put that into so your notes are not confused. But the concept is that if you have more unknowns than equations, you cannot determine the forces. This type is the same case. You have an X and a Y force, and here you have another force. Oh, I forgot to mention, this one also has a moment here. Okay, here's the same case, you have a moment here. So let's see, this is By, and this is a moment here. So in this case, you have a y and By equal to 0, but you have an unknown moment. So you have, also when you do summation of moments here, your unknowns will be summation of moments at A. Your unknowns are the moment and By. And summation of forces in Y, your unknowns are Ay and By. So you have three unknowns for two equations. You cannot find this case. Another one which is not known, which is the toughest one to deal with, is fixed beam in both cases. This is Ax, Bx, Ay. Let me clear that up. Ay, moment at A, and then you have Bx, By, and moment at B. So you have 1, 2, 3, 4, 5, 6 unknowns for only 3 equations, because summation of forces in X is one equation, summation of forces in X equal to 0 is one equation, summation of forces in Y equal to 0, it's another equation, summation of moments at any point is equal to 0 is a third equation, and if you want it, you can say there's a fourth equation at B equal to 0. So you have 4 equations, but you have 6 unknowns. Then this one is pretty tough. Okay, so this one, all these undeterminate methods use. This is a concept that is pretty interesting if you keep studying mechanical engineering and civil engineer, or only if you're curious. This is a macroscopic study. Statics analyzes the physics or studies the physics of a microscopic system. So we're looking from the system as a whole with very general concepts, like if the material is continuous, has no properties, the material, we don't care about the properties, we only care about the forces. We are assuming that it's gonna not is we're assuming it's not gonna break on those forces. So at that point, we only care about the external and some internal forces. But if you wanted to find the internal forces, then you have to use some microscopic methods where you go point by point, and some of them are finite elements or finite volumes or finite differences, which are numerical methods. Or you can try to obtain a partial differential equation and find the exact solution for it. So this type of examples, you need to know the boundary conditions. You need the forces to be able to solve anything internally. Okay, so after saying that, when we have, when we need to solve the problem, they're most likely going to be any of these three types, the first A, B, or C, simply supported, overhanging, or cantilever beam. And the new concept here is, as we know, we're going to have sections and see what the shear and moments are at those sections. So we know by now how to solve the external and internal forces of this body. We know that we have a P1 and a P2, a P3, and a W. This W2 is also a distributed forces. That this is also a distributed force that could be turned into a concentrated force. So this W2 will basically be a force somewhere. We can do moment at A. We can do summation of forces, find AY, BY, and we already know that AX equals 0. There's no other force there. But once we do that, the second step is to cut the material somewhere. In that cut, we decide where to do it, knowing the length. And from that point, we can find the shear and the moment. And the concept is that when you cut it, let's say they're telling us that, for example, we have a force at A that is negative 1880 Newton meter. This is not a force, this is a moment. And this is a force that is a negative force, 600 newtons. Okay, so and then we have a moment of 2880 Newton meters. So this is moment at A. This is moment at B. And this is a force at B, Y. So all those things show up once you start cutting sections, right? Because in order to cut this section, you have to analyze, okay, what is that force doing to the rest of the system? And that force is actually creating a moment with respect to A. And this force A is creating a moment with respect to B. So usually they're going to ask you to find that, but in this example, they're basically giving you the values so that you start getting familiar with how that would work. Okay, so for instance, this is pretty much what we mean. So in that example here at A, or this concept here at A, it's not an example really because we don't have numbers, because it's just in terms of PV and restrictions. But once we know the reactions, we can cut at point C and notice that we have a shear force opposite to the reaction force, and we assume a positive moment at that cut. Now the rest, so you know how you cut to the left hand side and you cut to the right hand side, left and right. So on the left you assume the positive moment, on the right you assume a negative moment. And of course that moment is the same, and this Well, and this cut is also the same. Sorry, the moment, I apologize. The moment is not the same. This is M prime, and the shear force is not the same, because now to find this force, you have to use the information from the right hand side. This is only the same if it's a symmetrical case, and that's not what we're given. We're not, unless P1 and P2 are the same and they're located at the same distance from A to the force and from the force to D, unless this is the same distance and this is the same length, this is the same distance and P1 equals P2, it will be symmetrical. Otherwise, the shear forces will vary. And that's precisely why you want to go and try to find your forces. You start cutting as many times as you want. So for instance, if you do another cut here, you have a V prime prime, which is different than V and V prime. You have a moment prime prime, etc. So depending on where you cut, you get a value. And that is intuitive because the deformation of the beam is different, is not uniform. It will be only uniform if you have a single force at the middle. Like for instance, in this case, this is the only case, or one of the only cases I can think of really, that you have a uniform shear force from right to left, because the force at A will be the same as the force at B. Let's see how that will play out. So if you have summation of forces at x equals 0, AX equals 0, and that is because this is a fixed point, and this is a roller, so we have By. So summation of forces at y equals AY plus BY minus P is equal to 0, right? And this point is, I'm picturing kind of like a 18-wheeler trailer carrying the bed, carrying some box, some some heavy duty equipment at the middle. The fixed point is actually the where the axis would be for the road, or for the tire, and this roller point will be the hinge where you would connect it to the truck, and you'll see some type of deformation like this that is uniform. This is how you expect this to, I'm exaggerating, right? But this is how you expect it to deform. Okay, it's symmetrical from this point to L half and L half. Okay, so you have 1, 2 unknowns, and you need another equation. Summation of moment at A is equal to By times L half L over 2 plus L over 2. So 2L over 2 is L, right? The distance between A and B is L, and this is a positive moment. And P is a negative moment, so P times L over 2. Therefore, well, they're giving us here the answer, but let's try to find it ourselves. By is equal to P L over 2 divided, this is By divided by, no, the By times L, so L is going to be dividing. Yeah, so By equals P over 2. And then from that, we can come to AY and say that AY is equal to P goes to the other side with a positive sign minus By, which is P halves, and 1 minus 1/2 is 1/2, so 1/2 of P is P over 2. So AY is also P over 2. Okay, we got that straight. Okay, so we have the reactions. Now we can cut, they're asking us to cut a C and E, which by now we know that is symmetrical. So the force, or the shear force at C and E, will be the same magnitude, but they could be different directions. So they teach us how to cut, and the first thing is that we decide what, well, they're telling us here at C, so x will be the distance that is between A and C. And the way you set this up is for AC, beam AC, you have AY minus, because it's positive, so minus the shear force V, it's equal to 0. So that's pretty simple because we know that AY is equal to V. Okay, perfect. Now the moment is pretty simple as well. So if we want to find the moment, we simply have to do a moment around A. So the reaction at A is cancelled. And this was summation of forces at Y equals 0. And then if we do summation of moment at A equals 0, taking counterclockwise positive, what we have is going to be V is negative. So V times X, whatever distance they give you. Here X is because they didn't give us a distance, but usually you'll know at what distance you want to do, unless you want to plot the whole shear force. And then there's going to be a negative moment plus M. This is equal to 0. So M is equal to V times X, but we said that V is equal to AY, and we said that AY is P over 2. So moment is equal to P over 2 times X. It's positive moment for this case. All right, now what we have to do is for AB. Or, sorry, not AB, but EB. What we have from EB is that the distance is L over 2 plus L over 2 is L minus X, because they didn't give us the distance. So distance is L. So summation of forces in X equals 0. We don't care about that one right now. Summation of forces in Y equals 0. We do care about that one. Reaction B is P over 2, so By. And we already took V negative for the first section. So now we have to do positive, because this is, Newton's law. If you take this force negative, in order for this to be statically sound, or V equal to 0, then there must be another force at that point, keeping it in a fixed point, or keeping it static. So this is going to be plus V equal to 0. We actually know what V is, so Vy is equal to negative V, and we know that By is P over 2. All right, we're going to need more room. So let's do moment. The moment is the same case. Since we took the first part positive, by convention, this is how they do it. Then by convention, also, you take the second half negative. So let's do here. Summation of moment around B equals 0. Then we have a negative moment plus this force P over 2, which is By, times the distance. So P over 2 L minus X. So again, this distance is used, or is given. So we're just using L minus X because we don't quite know, just to show that this is an arbitrary point. It could be very close to E, it could be very close to D. All right, so far we've only found the moments when we did the section. What they're showing us next is how to plot those forces. So if you start doing sections, you have your shear rate. I'm going to just replot this and explain. So the whole beam has a length L, and it's going on the x-axis positive, and we don't care about y anymore. What we care about is the variable. So, well, let's say that better. We do care about y, but the variable is shear. There's a force, which is a function of y. So the forces are on the y-axis. So just notice that the shear force is on the y-axis. Okay, let me write that down again. So this is a shear force and really is a function of y. Well, that's not correct, because if we're plotting, we should say is v as a function of x, right? This is correct because this is the variable that we're changing. But what I want you to realize is that v is the forces with respect to y. Okay, and again, that's called the shear force. We did not care about the tension anymore because the tension is basically zero since ax equals 0, since they didn't give us any boundary forces in the x direction. Okay, so the first thing we do is go back to the whole beam and we say, okay, what's the force at A? It's AY. What was that? That force is P over 2. So that's going to be a number, right? 10, 15, 3.7, whatever that is. So it's P over 2. In whatever units, newtons or pound force, whatever. Then they're telling us that V has the force. Let's go ahead. So AY equals V. So V is at C, so there's a point C. And that point C is V, well, hold on. P point C is at V. V is AY and Y is P over 2. Okay, so that point C is close to where the force is applied. And the force was applied at L over 2. So since V is tending to L over 2, and that is P over 2, then V is also P over 2. This is what I was saying, so it's symmetrical. So all this is the shear force from A to where the force is at P. All right, and then we have, at that point, we go to the next section, and the next section is E to B. E is very close to the point where the force is. E is tending to D. So we start by B. And B is also, it's also P over 2. So B is P over 2. So is either here or here. So this distance here is P over 2, or this distance is P over 2. Well, let's see. What is V? V, for that section, V prime, I would say, is negative P over 2. Okay, so it's negative P over 2. So V is negative P over 2. So how do we connect this point and that point? Well, that is where the force is, and the force is P. Ah, got it. So here we have a force of value P, and that is why we have P over 2 at V. Okay, so here at E we have V over 2, P over 2 I mean. Okay, so that's why it's negative P over 2. Okay, so we have negative P over 2. A point E tending to E is also P over 2 and negative, which is, this is our By, and we have to find our V. Did we find V? I think we did. Yeah, actually this is V prime. So let me write this down again. So By is equal to P over 2, and V prime, which is the point at E, is negative P over 2. All right, so that makes sense. So this is negative P over 2. Therefore, from this point to E is negative P over 2, and also to By, we're going to go straight because By is positive P over 2. So it goes back up. So I hope that I didn't confuse you by talking too much, but if you notice, there's basically two sections. If you were to draw it again in a more simple term, or simpler terms, you have three forces that you have to place. You have and two distances. Let's do it like this. Let's do it like this. So we have at L and L over 2. You have those two distances. If they give you more forces, then you have more distances. You have more sections. Each section is given by a force or by a moment. So we have three forces. One is at 0, and the value of that force is 8y, which is p over 2. Then we have another force that is p, and then we have another force that is p over 2. So this direction is positive, and this direction is negative, and this direction is positive. So ay, by, p, this is p over 2, this is p over 2. So simply connect the forces. All right, and that is how you get the amount of shear at any point. So if they ask you for a particular x, you can find that distance as a as a variable, that x, and find what the distance is, what the force is. So we know that for this particular case, at any distance between A and C, between A and D is this point where the force is located. Between A and D, you have the same shear force. And between D and B, you have the same shear force. But that's not always the case. In fact, this is the only case where it's completely symmetrical. All right, lastly, we have to plot the moment. And as you see, moment is not constant. It's a slope because it's a function of x. So this is basically, this has the form, if you notice, ax plus b. In this case, b is 0. But if you have a moment, then b will be that moment, and it will not start from 0. Moment has that shape as a ax plus b. Could be more complicated. If this is a distributed force, then this is not a straight line. This is, it's not a line. A uniform line is going to be, or how do you say that, is more like a curved line, a parabola, or some type of second order equation. So we'll see that in an example later. So let's plot the moment. So again, you have 3 points you have to plot. You have A, D, and B. Please locate those on your x-axis. So if you plot it, you have your A, your point where the force is, which is D, and your point B. All right, and the way you do this is from your moment. So C is very close to D, where we do the cut. That's the concept, extending to D, and that is px over 2. So is from A to D, when x equals to L over 2, the moment is P over 2 times L over 2, so is P L divided by 4. Okay, so that is this point, which they actually have it here, PL divided by 4. So this is equal to PL divided by 4 when x equals L half. That's the only, you do this for every force on your beam. You only have one force. When x equals to L, let's see what happens at B. You have moment equals P L minus L divided by 2, so this is 0. All right, so moment was actually pretty simple. The maximum moment is PL over 4. What do I mean over 2? It's over 4. I forgot how to multiply already. 2 times 2 is 4. And it decays. All right, so this is interesting because the maximum moment, as you can expect, is where the force is located, because moment is force times distance. And the force was applied at an L over 2. L over 2. Not 2L, but L over 2. So half of the beam distance. And then at that place, you have the maximum moment, which is positive. And you can tell that this is as well positive.